What does it take to build a war machine so advanced that it can evade radar, dominate the skies, and cost more than a luxury mansion per flight hour to operate? You're about to go inside one of the most guarded manufacturing ecosystems on Earth, where raw titanium becomes stealth skin, and innovation becomes the most feared fifth-generation fighter jet ever engineered. Welcome to the heart of the F-35 production line at Lockheed Martin in Fort Worth, Texas, U.S., where precision isn't a goal, it's survival. The F-35 program is the largest military aviation project in history. It produces three variants: the F-35A for Air Forces, the F-35B for vertical landing operations, and the F-35C for aircraft carriers. But despite the different versions, the DNA of each jet begins in the same place, a massive facility of robotics, composites, plasma cutters, and human expertise. This factory floor has delivered hundreds of aircraft for multiple branches of the U.S. military and allies, functioning as the central hub of final assembly. But today, we're not talking about missions or speed. Today, we explore creation, the engineering marvel, the supply chain, the materials, the assembly, the secret coatings, and the final tests before this jet earns its wings. From titanium frames to stealth coating, to an internal weapons bay that keeps missiles invisible, this entire journey is an orchestration of science, secrecy, and shockingly tight tolerances. So buckle up. The next time you see an F-35 scream overhead, you'll know exactly how it was born. Every F-35 starts as a concept on a digital thread, a shared 3D model used by engineers and suppliers worldwide. Its actual body begins with metal, mostly aluminum lithium alloys for lightweight strength, and titanium for critical structure and heat resistance. Titanium forms nearly 14% of the jet's weight, a necessary investment in durability. Major elements of the airframe rely on titanium sourced through global specialized mills. Once it arrives in the factory supply chain, it goes through chemical baths, ultrasonic inspections, and X-ray scanning to certify it has no impurities, cracks, or stress deformities. One microfracture could compromise a jet that pulls 9 G-force in combat. The main fuselage frame and bulkheads are formed using automated machining centers, some the size of train cars, shaving metal to extreme precision. The margins for error here aren't measured in millimeters, but microns. The result is the jet's skeleton, a metallic ribcage engineered to hold stealth panels, avionics, fuel tanks, and the F-135 engine, the power heart that gives the jet its roar. At this stage, the jet weighs tons but looks nothing like a fighter jet yet. Right now, it's simply a steel gray reminder that dominance begins with structure. Now comes the transformation stage. While the core is metal, 35% of the jet is composite material. These carbon fiber reinforced polymers are molded in climate-controlled clean rooms. Technicians wear suits like medical surgeons. The air is filtered. A smear of dust could distort the surface. The wings, control surfaces, and large sections of the fuselage are cured in autoclaves at incredibly high pressure and temperature, solidifying composite layers into hardened shapes. This manufacturing method creates panels that are lighter than metal, stronger than steel, and invisible to many radar signatures because they absorb electromagnetic waves instead of reflecting them. Stealth begins not with paint, but shape. Every panel edge is aligned like puzzle geometry so radar waves bounce away, not back. Special saws create panel seams so subtle they look laser drawn. This is where the jet begins to disappear, even while being constructed. You could stand 3 football fields away and radar might tell you nothing is there. This aircraft cannot be built with traditional bolts and eyeballing. Once the skeleton and panels are ready, the factory moves into laser-guided alignment. The entire jet body is suspended on assembly jigs while green coordinate lasers scan the airframe. Robotic arms begin drilling holes for fasteners, inserting bolts, and applying composite panel locks. Each fastener is tightened to a digitally verified torque setting, logged into the system forever. This allows future maintenance teams to know exactly what force holds each piece together. Thousands of bolts resemble constellations, but none are random. Every one is data, and now the jet gets its intelligence. Unlike 4th-gen jets that add tech later, the F-35 is born as a flying network node. Its distributed aperture system, helmet tracking, infrared vision, and sensor fusion computers are integrated now. Even components from Northrop Grumman for the center fuselage and radar system arrive ready for digital pairing. Over 300,000 lines of software code live inside this aircraft. Technicians plug wiring harnesses into the jet like arteries. Avionics bays are packed with computers, radio systems, ECM pods, and battle link equipment that communicate data to command centers, ships, drones, and satellites simultaneously. This is no longer just an aircraft. It is a battlefield operating system, time for muscle. The engine arrives separately, the monstrous F-135 turbofan capable of producing 28,000 pounds of thrust dry, and over 40,000 with afterburner. It is lowered into the airframe using overhead gantry cranes, aligned and locked into place. Now the jet has heartbeat. Unlike older jets that hang weapons outside, the F-35 swallows them inside. The internal bay doors are mounted and tested for hydraulic speed. Missiles, bombs, and cannons will live invisibly inside to maintain stealth. Here comes invisibility's final armor, radar-absorbent material. This isn't paint, it's a magic chemical skin sprayed in layers, sanded smooth, hand-checked, sprayed again. This coating adds millions to production cost but removes the aircraft from many surveillance radars. The surface is polished until it reflects nothing at the wrong angle. Factory workers call this phase the marriage line, where all pieces unite: canopy, landing gears, tires, refueling probe, tail fins, horizontal stabilizers, exhaust nozzle, AI flight control surfaces, all are mounted here. Thousands of inspections take place. Digital audit. Structural audit. Software sync. Pressure check. Seal verification. Fuel lines open. The ignition sequence roars. The jet shakes, engine power increases. The jet begins runway rolls without flight. At this moment, the F-35 finally leaves the ground, marking its first step as a true fighter jet. A highly trained test pilot climbs into the cockpit, carrying years of flight discipline and survival responsibility. The aircraft accelerates down a secured runway and lifts into the Texas sky. This flight isn't about combat, it's about validation. Every sensor, radar, electro-optical tracking, infrared scanners, and communication links is monitored in real time. The pilot pushes the jet through calculated turns, climbs, descents, and stability checks to evaluate maneuverability and flight control response. Engineers on the ground analyze live telemetry to confirm structural integrity, stealth performance, and system synchronization. This test determines airworthiness, ensuring the jet can handle extreme conditions, high G-forces, and digital warfare environments. The success of this flight signals that the fusion of human skill and American aerospace precision is complete. Flight data is checked. Combat systems verified. Helmet sensors calibrated. The aircraft receives its certification. Then delivery to military or allies. From a slab of titanium to a ghost of the sky, the F-35 isn't built, it's forged by design, perfected by data, and feared by outcome. If you ever doubted American manufacturing power, it's rolling down that runway, fueled by innovation, guarded by secrecy, and engineered to never fail. Thanks for watching. If you want more behind-the-scenes access into military aviation and fighter jet engineering, hit subscribe. The future is airborne, and now, you've seen where it starts.